we have actually developed the new technology that is the 4D printing, and then we also work on a lot of hybridizing the metal parts, which is like, for example, you want to have a small parts and then you want to also print bigger parts, and then how to take advantage of two different processes when it comes to the printing parameters. um, Another area that we actually work on, say example, you want to print clay, and then you also want to print some polymers. How to take advantage of using the same head, because at the technically you need a the head or stages to move go around for printing of the component. So we also have wire and then laser based additive manufacturing, where we can actually combine them together and then print the components. So this is another the work that we are working on when it comes to large scale components. So imagine you want to print a big component, without going for a tooling or without going for machining and so on, but you get the better in terms of surface finishing and so on. This is a laser. This has six different lasers, and then wire will be actually act as a raw material, and then it will be actually fused together, and layer by layer. So this is one of the finest, size of the parts that you can achieve, not just in terms of surface finishing, but also in terms of properties. And also, you can print a large scale component without much defects. Of course, there are post processings also. Um, just as I said, that is a brief about a few of the areas that we're working in. We do actually work many other aspect. You please visit the website and then get more information if you're interested in. So the 3D printing actually is not something very new or recently started. The first actually filed the first invention actually happened in somewhere in 1981 by one of the Japanese scientists, which is basically, you might have heard, rapid prototyping using photopolymers or so. Idea was use different resins and then you kind of cure it using a UV light or a laser. You kind of solidify, or you kind of form a layer by layer, and then later on, which is very most popular, the technology, which is also applied for printing of some of the devices, flexible electronic devices, or so many things, which is called stereolithography, that is SLA, or sometimes people also use it different terminologies. Since you might have heard a lot of the time SLA or STL. STL is actually short form of a stereolithography technique. So that's why they wanted to have some format. So they just extended the technology. I mean the technology into short form, that is called STL file. And then later on, SLS technology came, where one of the student at University of Texas actually developed this selective laser sintering. Much are more popular. The technology is FDM technology, which was actually invented in 1989 by Scott Crum. So when he actually invented, he also filed a patent, right? Once you file a patent, so you cannot actually reproduce the same technology. That's why, although the technology was there for more than 25 years, right, it was not popular till 2009 or 10. The reason being, you might have seen a lot of statistics, 3D printers, or you might have seen a lot of prototyping, or etc. Were not popular until 2005 or 9. But and then later on in 2009 and so on. So much of this patent were actually expired. That's where the revolution actually started. So that's where people have actually started using the technology and then reproducing it and then replicating. Also, there are a lot of open sources initiative started. Example, RepRap is one of the open resource where you can actually design, or you can actually completely design and then completely build a 3D printer by yourself. So because of this, all the patent got actually expired, and people started using open resources, and then the drastically the prices of 3D printing have actually come down, and then people were actually started using this technology in different places, because it is now affordable, and no more it is like costly business when it comes to polymer, at least. Of course there is still a high cost involved in when it comes to metal, but when it comes to polymer, it is now very much affordable. You can get it even less than 20,000 rupees a printer. So AM is also called additive manufacturing. So it's nothing but an automatic process of making any object or three-dimensional object from CAD file without using tools or fixtures, and then you actually print it. Like, unlike if you see the subtractive manufacturing, so there people uses a lot of tools, and then specific tools. Like example, you want to cut titanium, so you need to have specific tool for cutting titanium materials. Or similarly, when you change the material, like example aluminum, you need to have another tool to cut. But here, so you no need to worry about the tool part. You just build a material, and layer by layer, all that you need to form a nice slicing, and then get the, also people also called divide and then conquer. It's nothing but you kind of divide it and then kind of stack it, and then make a slices. And like if you see that subtractive manufacturing, initially you'll have an object, and then you actually cut it and remove that unwanted material, and then you kind of get the final component. Here you only adding the material, whatever the material is actually required. So most popular the format or process are actually you might have heard stereolithography. So of course there is another format, additive manufacturing format. It is basically extension of STL. If you see that STL only can actually store the geometric information, but not the material information per se. Like example, you want to have different properties, or you want to have different storing information, that you will not be able to do it. But in this case you can actually do when it comes to AMF. So it is also has some similarity when it comes to the CNC, or when it comes to the technology. Like example, as I said, you kind of slice it and then make a square, and then you actually combine it. So it is now fully automation. So why people actually prefer additive manufacturing? So as you see that even when it comes to that, why this is actually applicable for a semiconductor devices, right? So a lot of the customized component, a lot of prototyping is actually required for you to see how things are actually coming, whether your shapes are coming good, or whether your sizes are fine, or you want to see the touch of it and then feel it, right? So you can actually create complex geometries, and also you can actually embed a lot of multi materials, and you can actually come up with a new materials. And then, as I mentioned, new when it comes to low volume, like example, you just want to print one part, still it is affordable. But you imagine if you go for other technologies. Example, you talk about casting, you need to prepare first dies, right? For preparing dies, you need, again you need to go for a machining, right? So a lot of steps are actually involved to make a final component. So you actually kind of take advantage of a technology in terms of so if you see that like 10 years back, so not you will not find many softwares for using this like example, if at all you want to see the path plan, or you want to prepare your own CAD file. So those things were not readily available. Here you kind of get everything is now available on the internet, and then you kind of get open versions. Lot of library is available, how to build a component, and then how to prepare how to see the path plan, and then how to go about it. A lot of improvement actually happened in terms of automation, and then in terms of component and technology. So as I said, a lot of printable the library. When I say library, the information about, like example, you want to print a one component, say flexible electronics, or you want to have a few layers. And then what, like imagine you are using a TP or SL, I mean, or PLA. So you kind of get what is the temperature range of temperature that you need to work around. What is the basically temperature that you need to maintain for so many things. That, of course, another major for any technology that you want to grow. Major this thing is how industry actually accept, how government investments in terms of looking ahead technologies. So if you see that much of the countries, when you are actually good at manufacturing, so they go well ahead, because manufacturing is one of the main part of any product. If you talk about casting, or you talk about the molding, or you talk about injection cast, investment mold, or whatever. So all this manufacturing, basic manufacturing, actually will take you in a different route. So since a lot of freedom in terms of printing, and also, as I said in the beginning, so you most of the patents were actually expired, and now you can basically build your own printers, and then your own configuration, you get it and wrap, and then you can so a lot of momentum is there, and then people have actually accepted in different fields. That's where I think people in the semiconductor areas also, people have actually started using it. So one of the best example that I would like to see here, right? So example, if at all you want to prepare this cup, think about like how many steps that are actually involved for making, like if you go for a machining of this cup, it's a kind of a complex things are involved. You need to hold this object, and then you need to also look around, and then you need to print it. So many things are actually involved. It's not quite as straightforward, but in a one go you can actually print this kind of a component. So, but what is the major the difference when it comes to the one of the technology, which is subtractive manufacturing, right? So what happens in subtractive, you have a softwares, and then you have CAD softwares, and then NC, right? And you also have CAD software, and then rapid prototyping, also called AM software or AM machine. So here it is completely automation. Here it is not fully automated, because you also have a lot of tools are involved, and then you have a lot of other checks that need to be done before you actually make it. So that's why there is a huge gap or huge difference when it comes to CNC machining, which is after the G code, right? So this is one picture will actually will tell how different the technology. Like example, you take the material, and then you go for a subtractive manufacturing, and then you actually print, or you remove the lot of material, you can shoot a lot of the waste material here. But whereas in terms of 3D printing, you just use or feed how much ever the material is actually required, and then you get the less waste. Usually this waste comes as a support structure. Like example, you want to print at the top, so there you actually go for a printing of the material. So there are a lot of materials that are available today in terms of printing, and then in terms of how you can actually maintain the different temperature and the materials, or so on. This is basically overall the picture of how the steps actually that are actually involved in making the component, and making the whole the steps that are involved. Like example, processing the CAD file to and convert a steel file, and then transfer that file to machine, and then you, and also you need to also set up like what kind of materials, and then and so on. And then once you actually build the material, once you actually print the structure, and then remove, and then go for a post processing. So why actually what are the we need, what are the existing the technologies that were actually used in different fields. One of them actually is a selective laser sintering, so which is one of the process where you actually use a laser as a sintering, and then you kind of use to print a very high resolution component. And another technology which is I personally like, that is direct ink writing. So that the name itself suggests, So it is very flexible and then stretchable. People use it for flexible and then stretchable electronics, and also micro stereolithography. So that I will talk about these two technologies, because the first one is like more for when you go for say you have a lot of powder, because usually the select laser sintering works on a principle of a powder bed fusion, right? When you say powder bed fusion, you actually spread a lot of the powder and then you selectively melt the powder, right? Some of the components that are people are actually uses and then started printing up, example, integrated circuits and then diodes and then so many things that people uses for this technology. So as I said, one being a when it, like if you, that these two are the technologies are good on their own. Like example, semiconductor is the like backbone for electronics devices, right? And then similarly you have the manufacturing, 3D printing is like more flexible, right? So combining this, because the two are very emerging areas, emerging technologies that are actually happening, combining we can take a more advantage, and then speeding up the process, and then also speeding up the technology, also preparing your component. As I said, one of the advantage when it comes to 3D printing, right? Quickly you can actually achieve the component, or quickly you can actually print the product, right? So if you see that in a overall the technology point of view, right, or the printing technology point of view, right? One is you have the contact printing technologies that you might have seen, that screen printing and then flexography printing and then so many things, right? And similarly you have non-contact type, like example, one of them is being inject printing, right? So think about like you have a inject printing, right? And then you convert into that like a more of a multi-layer, or you also have aerosol jet printing or laser direct writing. So if you see that all these are maybe in an area or one dimension or two dimensional, right? You will be able to print. So now instead of two, you just add a multi nozzles to it, or a multi add a multiple layers on top of it, right? And then you actually create a three-dimensional object, right? So much of these things may work initially maybe just a few layers, but you increase the number of layers, or you basically increase the thickness of your films, right? Which will be maybe your flexible flexible electronics, or circuit devices, or whole casing, etc. So one of the the technology that basically people are using right and left when it comes to printing of this semiconductors devices, that is inkjet 3D printing. So this is one of the technology, so where people actually uses in terms of like they put different nozzles, right, and different heads. When I say different heads, so each, like imagine, think about, you have an inkjet printer at your office, right? And then you have different jets, right? And then you will be actually using different colors or different resin colors. Now think about using a different material instead of a different color cartridge, right? And then you basically increasing your thickness of film, right? Here when you see that inkjet printing, we will only see that the text which is basically on the A4 size sheet. And now instead of you just put one time, you increase the number of times the droplet deposition, right? So example, you make it like 10 times or 20 times, and then you actually form a layers, since it will have a tiny droplets, right? And then it will be easy to print the smallest part. Technically inkjet can print in a nano level. That's why this technology is so popular when it comes to the printing of electronic devices. So as I said, why people uses this technology, it is a high resolution, and then you can also print a micro scale, micrometer scale. So and you can actually also use a different say droplets, like different materials. Like you can basically use one nozzle for say conductive material, another nozzle for insulating, or another nozzle for different things. So basically, instead of we use a different color cartridge, now use a different material of a resin of that, like example conductive resin, right, insulating resin. So now you actually segregated, you basically control your parameters such a that, so you can actually put those materials in a controlled manner, and then you also design the whole the structure. So it is a cost effective in terms of printing, and of course you can actually also fabricate thin film transistors and the flexible electronics and then photovoltaic cell. So, and as I said, why, how they actually the forming, it's basically, as I said, you have a different heads, and then you have the different droplets will be actually sprayed, right? You have the different, and also sometimes you also need some kind of a post processing, right? And then you sometimes people uses different ways to cure it, and sometimes people use it post processing in terms of enhancing the printed part. Right here what they do, so they use a subtract, like say example on what surface they should print, because once you actually print, it will actually will stick to the bed, right? You also need to use some of the glass, or some of the wafers, or some of the where you can easily remove, right? So using you put a such a way that the surface, so after printing, usually you should remove it, and also you can control your droplets, right, ensuring your uniformity and then precise placement, right? And then post processing, just people say that sometime they get component may not be fully cured, right? In this case we actually go for post processing for curing of the materials, right? And to solidify the materials, as I said, one of the advantage when it comes to that 3D printing, so you can actually have a multi materials, and then you can print a multi layers, right? So this is basically the one of the printed the structure. As you can see, different nozzles, like one you have the graphene, and then you also have other two more different resins. So here, so they are actually using a different nozzles, right? Different nozzle, like example as I mentioned, you have a inkjet, and then you have different nozzles, and then you basically print whichever required, and then you give a control accordingly. I mean, you control your parameters such that only that material will come and then print. So that is one just example. So I will give you later on another few more examples. um, so another technology people actually uses, that is a VAT photopolymerization. So this is, as I said in the first slide, people uses this technology because uh, they use for photosensitive material, that is a polymer material. So where you can actually print layer by layer, since the technology is very good when it comes to printing of some of the flexible materials, or electronic devices. So idea is, again, there are few more within the photo polymerization, that is a stereolithography, digital light processing, continuous liquid interface. So what happens here, based on the the configuration, as I said, all these different technologies have come after the patent got expired. So here you actually use relay, I mean different light sources, like example some of them actually uses a UV light for curing the material. Some of them also use the micro lasers for curing. So very recently, of course the stereolithography is one of the oldest technology. So another one being digital light processing, which is a very recent trend, especially when you go for a printing of very precise and then very good surface, because it uses actually resin for printing. So as I said, there are different ways to print. So once you actually print or once you actually lay the material, you use the UV light laser as a selectively you melt it, or and then when it comes to DLP, which is basically not on a layered or point wise, it will actually will cure material, but it is actually area wise. Once you exposed, entire area will be actually cured. In example, you want to build a multi-layer of electronic devices, right? So entire layer you expose it, and then you can actually cure it. So another technology I said, light liquid in a crystal display, which is again you are also projecting it entire area, so that entire area will be actually cured. So this technology actually works on a basically light as an energy source. When you actually scan an entire region or layer, it will completely will actually will cure it, completely will solidify it, right? So this is actually the technology that I was of course, if you actually put this is a remove the resin, and then you put the say for SLS or selective laser sintering. So there they use actually powder, right? So here they use actually resin. That, but however, when it comes to that working principle, they're almost same. Why? Here they use actually the resin. Before you actually print, they spread the resin on the bed, and then they actually lowered on the platform. Similarly, when you go for SLS, so they do the similar, but only the difference there is they'll have another reservoir where your material will be actually coming every time. Here your liquid is already available, only your bed is actually going down as you actually deposit the material. So this is actually the very old machine that is available. And then this is like some of the printed parts using this technology, because if you see that these are the some of the precise the component or the surface finishing they expect in many of these applications. I'll just show you one video.
The SLA process is the oldest 3D printing process. It was created about 30 years ago, and it utilizes a 200 milliwatt laser, which is curing UV sensitive resin inside of a vat.
So you can see that the resin, and then you have the laser is actually going and then scanning it, right? And then it is actually curing entire, of course, here in this case you actually go for line based, but when it comes to that the DLP, it actually uses area wise, which I will cover in the next slides. Okay, so you can see that one of our big component. So they are actually prepared using SLA process. Okay, so of course, one major the difference between SLA and then DLP, which is I think very much will be useful in of this technology, is the idea is people actually go for point to point, right? And then here we actually go for when it comes to DLP, so you actually project entire area, right? To just to scan your the entire area, and then you can actually solidify it. So the steps are very this thing, like you kind of put the layer by layer, and then you slice it, and then you dip it again and again, so you wipe it. And so idea here is when you actually do this steps, like once you make one initial the step, you will be actually repeating entire the process. So there are different, but of course, what is the most important as when it comes to the semiconductor, this thing, the quality of your some of the components, like example, what kind of a material properties that you need to worry about it, or what kind of edge pattern, right, and then what kind of diameter of the beam, and then focal length, focusing point, and then fine tuning your some of the laser power. So this will actually will affect the quality of the part if you actually play with this parameter material properties, and then hatch patterns, and then diameter of the laser beam, and so on. So this is what I was actually talking about when it comes to the digital light, the processing. So you actually use the technology to, or you entirely scan it, right, entirely when you actually have the resin, and then you kind of scan it, and then you cure it in single go, unlike in the previous case where you are actually going point by point, and then you are actually curing it. So these are some of the components that are actually built and then using this technology. So I think I'll not go deep into this. Yeah. So these are some of the parts that are, we have this machine also at the Harvard. So if you're around, you're free to visit. So idea is why what is the advantage of this technology is basically it has increased the speed more than 5 or 6 times compared to the previous technology, and that is SLA, because it actually scans entire area, unlike you go by line. So when you see that, like as I said, I'll come back to the case studies of this example I was talking about, like how these two technologies are very much useful when it comes to printing of a small scale component, etc. So imagine you want to print a conductive filament, right, say at the top surface, one material here, you can see that different the materials, like example in this case you have a PLA, right, and then you also have the material will be like actually topped like a conductive PLA, right. So you basically change the material, the composition, right, and then how you also prepare it, right, once you actually integrate those material properties. So you use a different routes to a different 3D print, like example, whenever you actually change, or whenever you go for embedding the materials, like one of the technologies like FDM, right, so or inkjet. So these two are one of the easy to change the material instantly. PL is very common when it comes to the 3D printing of it. Now what they are actually trying here, so you are basically adding the multi materials, right, you can actually go for a or prepare a conductive filaments, right, and then you can actually feed it back, for 3D printing applications, right. I'm going to use a 3D printing for like example in this case. So you can again also print entire the part. Then you can actually add the rest of the. Sometime what happens, like you kind of a print of the part, and then you basically club it with the materials. So and then you can also, as I said, combine it with like example FDM 3D printer, right, where you can actually use once you actually prepare a filament using there are different routes. You can actually prepare a filament, right, like example, you can actually use the filament extruder, right. While extruding, you can also put a different composition of the materials, like you add some of the conductive the materials, and then you extrude the filament. Whichever the filament is basically extruded, so will have a basically conductive nature, right, conductive properties, right, and then you can actually feed it back. And then what is the major advantage, the challenge that you will have, what is the temperature that we need to maintain, what is basically the fusing temperature is actually required for us to print it. Like example in this case, 3D printed using FDM technology, that is a fused base. Also, you might have heard, a desktop 3D printer. So they have actually used, for a printing, simple, device, component. So before that, so they actually prepared, filament. And whenever you actually prepare a filament, so you can actually make sure what composition of the material. Like example, when you use the PLA, right, you also need to make sure how much amount of other material can be added, right? Like example, 20% or 30%, and what is the PLA material, right? And then that can be used at, right, like that. If you can actually control your materials, and then you can actually combine it, and then prepare the different materials. Similarly, so there are few more other applications which I'm pretty sure you will find a lot of the applications, because as I said, like example, you want to have some of the antennas printing, and then some of the PCBs, and then heaters, especially when you go for customized, or very or design specific. So you can actually use a different the technologies of 3D printing, where you can actually put precisely the how much the materials that you want. So as I said, here you can use it, either inkjet printing, or you may use it FDM. But idea is you need to correctly identify what the technology actually will work for you, right? Some of the other that technologies or applications that we have seen, how 3D printing can be applied. Example, micro electromechanical systems. Nowadays a lot of them are actually using 3D printing, be it be FDM technology, or inkjet, or so many things. And also a lot of actuators, and then micro, especially if at all you want to print some microfluidic devices, right? As you know that preparing any microfluidic channels are quite complex. So they do machining of the bottom layer, and then they put the top layer, and then they actually bind it using different binding materials, or a different screwing system. Instead of that, how to print create channels, right? And then basically you either use a different mechanism to print support structure, and then you remove the support structure after printing, because there are a support structure materials. Like example, wherever the channel and the top, if at all you want to print, right, you need to also have some materials. So there people, you can use it different dissolvable materials, so that you can actually remove after the printing of the materials. So you might have seen, there will be 2 3 layers, right, or 2 3 channels. So you can also have that different channels, and then different thicknesses, etc. And then most challenge part is like how you actually remove your support structure after printing, right? Of course, one of the advantage with respect to the technology, which is really good when it comes to the precision. And then you can also reduce a lot of manufacturing steps. Like you may think about, like if at all you want to print one microfluidic channel, right, you actually go for a lot of machining, and then you kind of need to have a you know devices to hold your components, and then you kind of machine it in a step by step. So that will take a lot of the time. Yet you don't need to worry about it, right? So another place, like a lot of application that we have found recently, packaging, and then interconnects, like especially when you actually go for print, I mean customization of each part, like when you are actually testing it. So not necessary every time you need to use it in a 3D printing, but multiple times whenever you want to print a small part, or quickly you want to see how it is actually coming. It may not necessarily that final component, but you can also get the feel of the physical part, right? So that you can actually go for actual printing. A lot of them actually uses also for getting initial prototypes, and then they go for actual applications. So a lot of packaging things, like example, you have the casing, right? You might have seen that once you get the standard casing, it may not fit all your entire smaller part can go into it, right? Now you immediately want to change the size of the casing, right? And now you want to quickly get the component, and then just go for FDM 3D printing, and then you can actually increase the volume of the casing or the dimensions, and then you actually print it. And also a lot of customized interconnects. So and then you kind of integrate your PCBs with additive techniques. There again, a lot of techniques that are actually available today, like FDM technology, that is fused based deposition, which is desktop based 3D printers. And then you also have so other the technologies in terms of resin based, so on, right? So and then one of the issue that we have seen very recently, the thermal management of a component, right? So whenever you actually print a component, or whenever you place any component, how effectively you can actually discharge, or how effectively you can actually heat dissipation will happen. Otherwise your entire that device will be like will not be efficient, or either it will destroy over the time. So how effectively you can actually control, like example, can we also print some of the heat sinks? In fact, some of our students actually printed some of this heat sinks, so that so they have actually seen some of the improvement. Of course, a lot of this heat sinks were actually made up of aluminum. Still, printing of aluminum with a typical 3D printer is still challenging, and a lot of research work is going on. So idea is how you can actually use 3D printing for this application, so that you can quickly see the prototype, or quickly you can see the final the component. Most importantly, you can actually always change your designs, and then you can actually see the component, this thing. Of course, the challenges that I always find any technology, right? Finding the right the technology, finding the right machines, and then like what kind of properties that you are actually looking, and then what is the scale that you are actually looking at. Like example, I always tell, so if you know the 3D printing, that doesn't mean that you can actually apply everywhere. You should know that exactly where to apply, and then what your expectations. So and then what is the level of size that you are actually looking for. One of the major challenge when it comes to semiconductors. So printing a smaller component is what important. So you need to identify whether your SLA will work, or most of the time people actually use a inkjet 3D printer for going for a nanometers, etc. So of course, so you need to see like whenever you go for multi nozzles, or multiple droplet. I mean droplets, multi nozzles, etc. So you need to also think about like how to control it, and then how to streamline it, and then so on. Since a lot of cost, and then especially when you go for advanced technology, so you need to think about, do you really need or how effective or efficient in terms of producing the component. So of course, the trends that I could see, that like how people are actually looking at so example, how you can actually also apply some of the AI driven design. So optimization of, like example, if at all you want to print, or how are you are actually optimizing, and then go for 3D printing. And also, as I said, one of the trend, nano 3D printing for semiconductor applications, right, is one of the major trend is actually happening. Because as I said, 3D printing actually proven when it comes to the components ranging from, say, from mms to meters, right? Like you can actually print anywhere 5 meter or 2 meter large component. You can also print a very good in terms of like example powder bed fusion or SLA or FDM technology. So they have actually already established say if you are to print 500 by 500 or 200 by 200, but more challenge in terms of a printing for a nano scales, which is you need to also have that controls, like example the how precisely your stages, right, how precisely you can actually control your stages, so that you can actually print a component at nano scale. Of course another the technology or other which always actually takes things higher, that is hybrid manufacturing processes, like example how to combine it, like you might have seen a lot of the parts also needs combining these technologies, example additive and then subtractive, so that you can actually go for better in terms of surface finishing, and then as well as in terms of as you know that if at all you want to have a good surface finishing, CNC has proven better surface finishing. But whereas when it comes to the quickly achieving a component, maybe additive is like proven, but and then surface is like compromised, right? How to actually take the advantage of two, one is really good at surface finishing, one is really good at printing, right? And now you combine it, and then you make a good the component. So I think that's all from my side. I think we'll just take another 10 minutes for the discussion.
This is Karthikeyan, sir. Actually, I'm working on PLA composites on the additive manufacturing itself. On additive manufacturing, sir, that is what my proposed work for PhD.
Mm-hmm.
Actually, as you told that polylactic acid, which is a biodegradable composite which cannot be used in stereolithography, and is there any alternative like the polymer PLA filled with any some fillers like biochar or something can be used as a can be powdered and used as a feedstock material for SLM, sir?
So SLS actually proven. So already,
Yes.
like example, what see there is a two technologies. One is SLM and then SLS, right? So that is the selective laser sintering and then selective laser melting. So selective laser sintering. So you can also actually apply for a polymers. But whereas selective lasers melting, you can only apply for metal, because there you are completely melting the material. Like example, imagine you have a powder particle, right? So you will be completely melting the powder particle, and then phase transformation itself will happen there, right? But whereas in selective laser sintering, you are not actually completely melting your powder, which is the good for when it comes to polymer, because in the polymer part you actually no need to melt completely, because if you try to melt completely, chances are that it will just evaporate, right? So to avoid that, you basically just allow to neck formation, right? Just to give little heat or little or I mean laser such a way that laser power such a way that it will only neck formation will happen. You may be aware of metallurgy part, like necking formation, and then further if you increase the temperature, and then it will actually form entire phase transformation will actually will happen. So you don't need to allow the phase transformation, but you allow only to neck formation. So there you basically make sure you only just sinter the component, not melt the component. So now, how to crush it, your polymer, right? You may have to use a different routes to crush into smaller particles. Like example, usually the powder particles may ranging from 140 to 150 microns, right? If you actually use a different techniques to crush your powder particles, I think it is doable. But again, proven when it comes to the PLA, you go for another method. You use any filament extruder, right? So and then go for a post processing of it. Like example, you use a PLA and then different other elements. Like when you actually extrude the filament, you add the other metal powders or other conductive or whatever metal that you want to actually add it. So and then now you extrude the filament using filament extruder. Don't confuse a filament extruder with you also have the another extruder while printing. That is different. Printing extruder is different from filament extruder. Filament extruder is actually will help us preparing a filaments for 3D printing. Whereas filament that you might have seen, the nozzle extruder will basically will help us printing during the printing. So these are two different, right? So you may actually try with these two options. I hope I have answered your question. Yeah, could you hear me?
Thank you very much, sir.
Yeah, okay.
Yes, sir.
Okay, I mean, if there are no questions, I think even after the session, you can reach me out. You can take my contact from Dr. Kiran. So I'll be happy to answer even after the meeting. Of course, I could not cover many things because of the time. Also, but I'll be very happy to answer if you have any questions over the email.
So thank you once again for your informative and engaging presentation, sir. We are very grateful for your contribution to our FDP.